Is this in your notes or no? It is? Okay. So this, I don't know if this probably should look a little familiar to you. This and what's on the board, Emily and Rylan, are the same process, just different starting points. So on Friday and Monday, we did a titration of a weak acid with a strong base. Okay? The same four steps are very similar. It's just we're starting with different stuff. When we were doing titrations of a weak acid, before we added any of our strong base, we just treated it like a weak acid problem, right? And then we had a series of buffers that were before the equivalence point. Then at the equivalence point is where we flip from our weak acid to our weak base. This is where we flip from our weak base to our weak acid. Are you seeing it? Okay, and then beyond the equivalence point is now where we are treating it like a weak or a strong acid problem, or not exactly like a strong acid problem, but you are just focusing on the strong acid. Does that make sense? If we have time, I want to come back and do this problem and maybe just highlight one of each of these points. But since it's the same process as what we did on Thursday or Friday and Monday, I'm going to skip that, and if we have time, we'll come back to it. What I want to spend the most of today doing is strong titrations. These, again, are going to be the easier of the two, I think. But it's the one we probably spend the least amount of time working on, and so sometimes when it comes up on a test, we struggle a little bit. Okay? The reason why I say this is the easier of the two is in yesterday and a couple days before when we were doing a weak acid and we added a strong base, we got this. This is our equation yesterday when we had a weak acid and added a strong base to it. What did we essentially do? We took a strong base and converted it into a what? Weak base. Okay? When we do strong situations, we are taking a strong acid and a strong base, and we are producing a neutral salt and what? Water. So when we were doing this situation, we always ended up with either an acid or a base. When we do a strong situation, we always end up with a neutral salt and water, which makes it a little bit easier when we're doing our titration steps. Does that make sense? So, this is what it's going to look like. All right, so I guess I'm just making up numbers here. Let's do first situation. Let's say that we have not added any of the NaOH. How are we going to treat this problem? I'm going to treat it like a strong acid problem. Well, gosh, that's easy. How do we do it? Yeah? Strong acid, what's it going to do? Completely dissociate. So we know the H plus concentration because it completely dissociates. Negative log of that. Voila, we are done. Okay, easy enough. All right, let's go on to where we have added some amount, and let's just say I add 10 milliliters. Write small, if you will, because we will use most of this page or space that you have. Now this is where it's a little bit different. It's not quite like a buffer problem, but we still have to do stoichiometry. So, instead of putting HCl plus NaOH produces salt and water, can I just do this and you guys understand what I'm doing? If it's a strong acid or a strong base, because a strong acid gives off this, a strong base gives off this. These are the only things we're really worried about, right? If you want me to go put the whole equation, I can. But this just makes less clutter, I guess. Everybody understand why I'm just doing this? Because does the salt participate at all in figuring out the pH? And all we're worried about for pH purposes are these, right? Yeah, and since it completely dissociates, all we need to do then is do our stoichiometry. Because we know that it completely neutralizes it, doesn't turn into some weak form like it did in the weak acid, weak base problems. Alright? So we got to figure out the millimoles, right? Okay? For our acid, 50 times 0.2 will give me we'll need 10 millimoles. And I added 10 milliliters of NaOH, so 10 times 0.1 give me 1 millimole. Do my stoichiometry. Subtract 1. Do I care how much millimoles of water is produced? No. All I want to know is, I neutralize my strong base that I added, and I have a certain amount of strong acid left. Do I have to do Henderson-Hasselbalch equation? No, it's not a buffer problem. I just need to find the concentration, take negative log of it. However, is this concentration? No, but I can quickly get the concentration by taking 9 millimoles and dividing by what? Total volume, though. I have 50, and I put in what? I put in 10, so my total volume is 60. I'll write 50 plus 10 so that we kind of understand where that comes from. Following so far? Okay.
So you don't add anything to H2O,
Well, you can think of it that way, or you can think of it as it's pretty much neutral properties, right? All I really want to know, if we're trying to find pH, is I need to know this, right? When I'm finding pH, H plus concentration is all I'm worried about. It takes more work to get the H plus concentration when we're doing those other types of problems. When you do this, you should get 0.15. And then to find the pH, you do what? Gives me what? All right. Okay, I'm going to do I'm only gonna do one more before the equivalence point here. I'm gonna have you guys do it. We'll go 50 milliliters at it.
Are you just making up these?
Yeah. Normally they will tell you how much, like, at what volume added you're supposed to find pH of. Yeah, I'm just coming up with random ones. So like in the previous problem, we had a whole list of volumes that we added. So this one I'm just coming up with random ones. All right, so I want you guys, it's treated just like number 2 here. You gotta do your stoichiometry, find your molarity with the total volume, and you're done.
Is this the last one?
Is this the last one we're doing? No, we'll probably do 2 more. What do you
For this
mean?
problem?
Yeah. Maybe 3 more.
Why?
Why?
Yeah.
Why not?
What is this thing?
What do you mean, what is this doing?
We don't know what titrations are.
Sure,
We missed that.
of course. And that's your job to figure that out.
We'll hopefully when we get home.
Okay. What? Aka of strong acid.
So is there no midpoint here?
I mean, you could call this the midpoint, but it's not like a buffer problem where you plug in and you just know pH is pKa.
Yeah.
So technically, this would be called the midpoint, but
It's not what
so like I still have my 10 of my acid, and then you'll find that you have 5 millimoles of your base, which in the problems we did the past couple days, we knew that was the midpoint, so we knew that the ratio of conjugate acid, conjugate base was 1. But are we producing a conjugate here? No, because this is a strong. So we're not converting some strong version to something weak, we are completely neutralizing it. So -5, -5. Full volume. What was that? Negative log of that. Okay. So we have 4 kind of points here that we're going to focus on. I did 2 before the equivalence point because I just want you to realize that anytime you're after you've added, but before the equivalence point, process is the same. Okay? Step 4 is at the equivalence point. And those of you who are here, what does at the equivalence point tell us? Or what's going on at the equivalence point?
Acid base.
Yeah, the acids and bases are neutralized. In a weak acid, weak base problem, we knew that the pH was either above 7 or below 7 because we took a weak or a strong form and converted it to a weak form. But are we converting any, do we have any conjugate that we're being produced here? So what's your pH? 7. Right? I'll have 10 millimoles and 10 millimoles. They'll cancel each other out, producing water and a neutral salt. What's my pH? And I'll just write quickly here that you have 10 millimoles of this, and 10 millimoles of this. Oops, this is the M. Okay, those completely neutralize. Giving you a pH of 7. Right? So we've got before we've added, before the equivalence point, at the equivalence point, I'll do 1 point beyond the equivalence point. Okay?
There's 7.
Okay? We've only got so much of our weak or our strong acid, and we said we had 10 millimoles of that, right? Correct? Now let's say that we have added, let's see, 150 milliliters of my NaOH. 150 times 0.1 is how many millimoles? 15. So now what becomes the limiting reactant?
The other one.
Alright? After we should have 0 and 5. Okay, process is still similar. I still want to find the concentration. Total volume is what? 200? What is that the concentration of? Okay, since that's the concentration of OH, we have to find the H plus before we can find the pH. Or pOH 14 minus that. Whatever you prefer.
It's shorter for derivatives. Find the pOH.
And that's what I did the past couple days too. So
12.4.
So 14 minus 1.6 is 12.4. So, in both all the weak stuff we did the past 2 days and the strong stuff we did today, we really still have 4 locations. We have before anything's added, we have before the equivalence point, we have at the equivalence point, and we have after the equivalence point. Those are our 4 locations. Now, are they a little bit different when you do the strong acid, strong base? A little bit, but same idea. Okay? Before anything was added, we treated it as it was just a strong problem. And since we started with the strong acid, we treated it like a strong acid problem. After we added, but before the equivalence point, we just had to neutralize our stuff and figure out the concentration to get our pH. At the equivalence point, we knew that we completely neutralized everything, producing pure water, pH of 7. Beyond the equivalence point, we now flip from acid to base. Being our important thing, same process. Okay? let's do this one. This one will be short, but it's kind of the practical purpose of all of this. Now, up to this point, we have just been taking and doing a titration just to kind of see what every little spot in the titration is going to look like, what the pH curve is going to come out to be. But we, at the very beginning or onset of doing these titration problems, I said usually the purpose of a titration is to what? Those of you who are here. You remember? The purpose of a titration usually is to you're probably not going to find it in your notes. I just said it. No, you don't remember? Usually the purpose of a titration is to figure out the concentration of an unknown acid or to figure out what your unknown substance is. Since you know that acids and bases neutralize each other, you can use a known concentration to figure out something that's unknown, and that's what we're doing in this problem. A chemist has synthesized some acid that we do not know what it is and wants to know its Ka value. If they know their Ka value, can you maybe at least narrow it down to maybe a couple acids that unknown could be, and maybe even narrow it down enough to know exactly what that acid is? To do so, the chemist dissolves, doesn't know what the acid is, but it can dissolve a certain amount of that acid in water and titrates it with a known concentration of a strong base. He finds that after adding 20 milliliters of NaOH, that the pH is 6. It wants us to find the Ka. So what we have is an unknown acid reacting with a strong base to produce an unknown conjugate base and water. That's what we know. Here's also what we know. We know the concentration of my, or not the concentration, we know the number of millimoles of my unknown acid. And after we added 20 milliliters of 0.05 molar NaOH, couldn't we figure out the millimoles of my strong base? Millimole. Now we can use this logic to know that our strong base is going to completely react. Leaving us with 1 millimole of my unknown acid and 1 millimole of my unknown conjugate base. Any ideas what we would do from here? Those of you who have been kind of around the past couple of days.
You can find the H plus concentration.
Could. It's just the midpoint. That's nice. That's a good thing to identify. Absolutely. How do you know? Equal amounts of conjugate. pH, we said, is 6 equals the pKa. So pKa should equal 6. If we know the pKa is 6, can we find the Ka?
What's the
10 to the,
oh,
right?
negative, right?
Yeah.
One is negative.
So it should be 1 times 10 to the negative 6 is our Ka value of my unknown acid. Now, someone in a lab could see that and go, oh, I can pull out my handy dandy 102nd edition chemistry and physics handbook, find my list of acids with all their Ka values, and definitely at least narrow it down to a couple possibilities, probably even figuring out exactly what that acid is. You don't think there are some practical purposes or uses for that, potentially in some commercial production plant or trying to figure out something? Absolutely. Yeah, that's what I'm talking about. That's what I'm talking about, sure. Okay?
Where did you get 6?
pH of 6 or pKa of 6?
Told us.
So why did we have
Why do we have to what?
to do
To check, make sure that.
Well, you had to know it was at the midpoint. You wouldn't have known it was at the midpoint until you did this. If you don't know it's at the midpoint, you cannot say pH and pKa are equal. Which that's part of what we spent a bunch of time doing on Friday and Monday, was identifying the stages in a titration. Why is it important to know the stages in a titration? So that you can practically use it to solve some unknown stuff. If you don't know the stages of the titration, you're not going to be able to do something like this. Does that make sense? You wouldn't have been able to say, oh, I know that my unknown acid is going to completely react with my strong base to produce its conjugate. You wouldn't have been able to identify that it was a 1-to-1 ratio or when you have your midpoint, because we know that a pH equals pKa log of a 1-to-1 ratio. Log of 1 is what? 0. So when we're at the midpoint, we know the pH is equal to the pKa. Okay. And even if we weren't at the midpoint, I still could put the log of two numbers and still solve for the pKa, right? If this wasn't log of 1, I still would have had numbers here that I could have plugged in and solved for, manipulated the equation to find pKa. I just used the midpoint because it was quicker. That makes sense? Okay. So I don't know what your problems are going to look like in your homework. My guess is you will have one similar to this. You will have a strong, strong, and you're probably going to have a weak base, strong acid one. I can look quick. What is your homework? 51 looks like a strong, strong. 53 you said? 55? Ooh, that's a lot of work. 55 looks like a weak acid, strong base. And then what was the last one? 59? It's like a combination of many different titration problems, either weak acid, weak base, or it looks like A is a weak acid, B is a weak base, and C is a strong, strong. But they're only asking you for 1 point, not, hey, solve for, 10 different points on the titration curve. Does that make sense? Okay? Last question.
For on number 59, talk to the pH at the halfway point. But
On number what?
9, this one right here. It gives you Ka, so the first half should really be. It says Ka, so talk to pH at halfway. Is that the midpoint? So wouldn't that the first half of the pitch problem is 3?
Yes.
Okay, but it's an equivalence.
Yeah, the equivalence point can be more difficult. But it's going to be a little bit different if you've got a weak, well, no. Well, yes. If you're dealing with a weak base, you're going to have to take that KB, turn it into KA, or take the negative lot of that. All right. If you have questions, I'm here after school, especially for those of you who were gone. I have the videos posted. I have played Practice till 5. I get it. Part of what you have to, you know. I'm not trying to be a mean. If you're gone, that's part of the deal.